Sweet. So from wind energy to solar energy. So kia ora koutou, my name's Shreyas. I'm going to be talking about solar energy and in particular a methodology for estimating rooftop solar energy potential. And so when we talk about solar energy potential, we're talking about total irradiance across the entire rooftop. And so you would take those numbers and apply conversion factors for things like the types of solar panels and inverters that you install. So just a quick about me. I worked in some software engineering roles for 8 years, most recently as a senior engineer at KiwiBank. This year I decided to study GIS at a master's level at the University of Canterbury. Crucially, I'm not an energy systems specialist, but it's been pretty fascinating to hear a lot of the talks over the last few days, just as it's all been new information to me. So yeah, really grateful to be here and able to hear all the talks. I thought I'd talk about some context that I found interesting while doing some research for this project. So in Australia, you have a couple of states, over 50% of households with solar energy, and 21% of energy production in the past year has been through solar. Pakistan has been in the news quite recently as they've started importing huge amounts of solar panels in 2024, more than all of Africa. And they're also on track to account for about a fifth of energy generated through solar in 2026. And so this creates some interesting conundrums around the economics of the grid, including how do they deal with that huge demand loss from people installing solar panels and generating electricity through that. And if you're interested, there's an article from Dawn that kind of talks about the economics of that. So in New Zealand, 1% of our electricity generation was solar in 2024, and then forecasts are suggesting up to 6% in 2035. So we know that solar panels are getting cheaper. We know that the amount of solar radiance coming from the sun isn't changing, and in fact, some climate models are predicting less cloud cover in New Zealand. And so my project, which is working with Rewiring Aotearoa, which I'm sure a lot of you are familiar with, they're interested in like a national level data set of solar radiance across the country to help talk about differences in the region using accurate estimates of solar radiance. So I've kind of mashed that into a research question, which is mostly just objectives, but I guess I'm looking at accurate and validated estimates of rooftop solar energy potential at different scales. So community level, suburb level, as well as whole city levels, usable by different stakeholders, and the methodology is aimed to be open and reproducible. So I've just highlighted some of the parts in the title I've given this master's project, which is a bit wordy, but I'll just be talking about the methodology and about these things in particular. So the whole methodology is really underpinned by something called LiDAR DSM, so LiDAR digital surface models. And so this is a data set created by planes flying over an area, shooting laser beams at the surface of the Earth, and you can develop a model from that. And so this data is provided free and open source by LINS. And the picture there shows the coverage of LiDAR that we have in New Zealand, and it's really good. So we have 1 meter by 1 meter resolution data for all of the darker areas, which is mostly all the urban areas. And so with a square meter resolution, each sort of pixel in the data set represents a square meter, and this is good enough resolution to capture things like tall trees and buildings, and what we're interested in, rooftops as well. And so as a result, digital surface models are quite a popular input for estimating solar irradiance. And so we use GIS, or Geographical Information Systems, software to manage these data sets. So raster data, which is for example, the digital surface model, vectors, which are like building outlines that we can use to clip the digital surface model, so we only get building outlines. And crucially, the solar radiation estimation as well has been developed in these tools. And so GRASS and QGIS are both free and open source tools that we used throughout this methodology. Like I mentioned before, open source, so all of the code that we've written for this, which is in Python, is under the MIT license. So you're free to take this code and do whatever you'd like with it. And so we really want this whole methodology to be replicable. We want to increase transparency in the model used to estimate solar irradiance, because it's not always clear how irradiance is estimated for a lot of things like providing quotes to households. And we also want to invite more contributors to help develop this model as well. So I thought today I'd talk through a work example just to show visually how this methodology works. So this is a digital surface model, like a visual representation of it. Can anyone tell me what these buildings are? No one. Okay, well, we're about here. So this is a few buildings in the Otago University campus. So that's the business school in that on my right side. So you can see that some pixels are lighter than others. That indicates height. So this digital surface model, its value represents height. So the business school roof is quite tall. From this data set, you can derive two more data sets. So on the left is slope and on the right is aspect. So with slope, the values go from 0 to 90 to represent each pixel and how much they slope, basically. So all the outlines of the buildings are in white because that represents a 90-degree drop-off. For the aspect, it's a bit harder to see because the values go from 0 to 360 to represent which orientation on the compass it's facing. And so 0 and 360 are like the same because they're both north. So yeah, it's a bit harder to see. But with those three data sets that we now have, you actually have enough to measure solar irradiance. So this is a estimate for January. I haven't included any good cartographic elements just because it's more of a visual thing, but all the bits in blue are low irradiance. So all the stuff in between buildings is in blue. I wanted to highlight this section here where you can see like a red to white gradient. That's because this part of the business school shades the rooftop surface in the mornings. So all the sun from the east is kind of shaded. So that's why you kind of get a gradient. So cool thing is with this, you get shading built in and you don't have to worry too much about manually adding buildings or trees to work out shading. So from there, you can then filter out low performing pixels. So maybe pixels that don't receive a certain amount of kilowatt hour radiance. You might also want to eliminate pixels that have a slope that's too high because you can't install panels on them. You might want to remove certain south-facing pixels as well. So with that, and then you can also clip the whole data set to just building outlines, which is what is shown here, because we're just interested in the rooftop surfaces. And with those kind of numbers and estimates that we now have, so those are clear sky estimates, so assuming no cloud cover. Part of this methodology is going to be using weather research and forecasting data, which is a hindcast of solar radiation with a fairly coarse 4-kilometer resolution, which is based off of Error 5 reanalysis, which is sort of looking at the worldwide scale of solar radiation values. And so with that sort of data set, you could then average the last 5 years to get a typical scenario of solar radiation numbers that have been estimated. And so the whole idea of that is we can then provide a sort of proxy for the amount of cloud cover because the values provided by these hindcasts would account for atmospheric conditions. So combining all that, this is just sort of a table summarizing the different, I guess, aspects of the methodology. So for the business school, you have an area of about 3,000 square meters, the usable area after you've done the filtering around 1,800. And so in January and July, you can work out the clear sky estimates, as well as the estimates coming from the solar radiation climate models. And as an example, for the cloud cover loss, you're looking at about 3% in summer, which is pretty low. And then in July, yeah, you lose quite a bit of energy due to cloud cover. One thing I want to notice was the factor of about 4 going from summer to winter, as I think Philip yesterday was mentioning that that's about the amount of energy you lose between summer and winter. So yeah, and then this is just the visual comparison. So using the same scale, 0 to 300,000 watt hours, it's quite a stark difference from summer to winter, which we kind of all know with solar energy. So the use cases of this whole methodology for households, we can do things like estimate worst case weather scenarios. So we can look back at previous years and find like the worst performing winters, and then run the whole methodology and then understand how we might account for lower irradiance in winter. For panel installers, they get access to raw solar irradiance with shading already built in. So it kind of simplifies the workflow of having to model the customer's kind of rooftop and add shading and stuff. So they get access to that. For councils, because we're using building data sets to kind of clip the solar irradiance data, we can also delineate by building type. So councils might want to know things like car parks or their own holdings, how much irradiance and subsequently solar energy could they produce from their buildings. And so as I mentioned, I've been working with Rewiring on this, and we've sort of formed a bit of a community around it so far. So we're looking at collecting real-world solar panel installation data and performance. There's also some people looking at database schema design. Rafferty, who's also attending, he's been helping us set up reproducible environments so that we can distribute the computational load, because most people's computers or laptops these days are pretty powerful and can run some of the computation involved with this, even if LiDAR digital surface models are quite intensive computational wise. So I thought I'd end with a bit of a call to action. If you've got ideas, ambitions, or feedback based on what you've seen, or you're skilled in GIS programming or data science, or you're from the energy industry and you're interested in how some of this methodology might be of use, feel free to get in contact with me. There's also a code on GitHub if anyone's interested in looking at that. Cool, thanks for listening.
Thanks, that's really interesting. Questions?
So just really interesting stuff. Tilt angle and kind of profiles over the day. Is that an output? Or?
Yeah, so I think so with this methodology, because I'm doing a master's summer project, the scope is pretty limited in terms of what I can produce. But I think the kind of next steps is to start looking at the different characteristics of solar panels and understanding how you would then take some of these irradiance numbers and then how they would perform against certain panel installations. That's like a whole challenge in its own thing. Like, you know, how many of these panels can you fit on a rooftop? And then, yeah, over time, how tilt would affect that. But the cool thing is because we can define the granularity of time that we're doing these estimates for. So we can say, take a measurement every 10 minutes, 15 minutes. We get access to a whole time series of data throughout the day. And then so if you wanted to say, if we change the tilt of these pixels by this amount, you could do that because it's all just data that we can run, we can do like arithmetic on. So we could take a chunk of it, change the orientation, and then see how much energy would then hit it over a certain period of time. So I think the benefit of this methodology is that it's pretty flexible in terms of being able to change a whole lot of parameters. Yeah.